INAE and a fellow of AAIA. Our talk today is on a very interesting topic of agentic problem solving, intelligent agents, and adaptive and autonomous decision making, which is roughly is the abstract which is given. It's a short abstract. I'm just reading it out. Agentic AI represents the next frontier in artificial intelligence, where systems are designed to perceive, reason, and act autonomously in dynamic environment. This talk explores the core principles of agentic AI, artificial intelligence, including intelligent perception, autonomous reasoning, and adaptive execution. She will discuss key architecture, problem-solving strategies, and a few real-world applications. Professor Deepika De, is a professor of computer science at Ashoka University. Prior to joining Ashoka, she was the chief scientist at Tata Consultancy Service Research, where she was heading research in the themes of economic and financial intelligence and real-time context-aware enterprises. Deepika was earlier a member of faculty at the Department of Mathematics, Indian Institute of Technology, Delhi. Deepika has been elected to the Fellowship of Indian National Academy of Engineering in 2021. She was also awarded the Distinguished Scientist Award by TCS in 2012. She has served as program committee members for several conferences like AAAI, KDD, etc. Deepika has a PhD in computer science and engineering from IIT Kharagpur, where she had also done her graduation and post-graduation in mathematics and computer science. Deepika has been an active member of Association for Computing Machinery, SCM, for more than a decade, besides serving the committee of SCMW, I believe actually stands for Women in India. She also mentors young researchers and faculty in areas of computer science under the aegis of SCM India. She is currently serving as an eminent speaker. It is really a great honor for all of us in having a distinguished person like Professor Deepika De as the speaker here. And it is further heartening to know that she is also from my alma mater, that is IIT Kharagpur. Okay. So with this few words, now I'll request Professor De to make her presentation. Professor Deepika De, please.
Thank you very much for the kind introduction, and thank you for giving me this opportunity. So I'll just switch to my slides. Is it okay if I switch off the video just for bandwidth preservation?
Okay.
Okay, so yeah. Okay, I hope it's visible in.
It is visible, Pakka.
Okay, yeah. So good evening, everybody. And what I think today, everyone is quite aware of the rise of AI agents, where we are not only talking of the AI capability to handle unstructured data as opposed to numbers only, unstructured data as in image, video, text, but also we are talking about AI taking over all kinds of generation tasks, like AI will write programs itself. Now, how will it write programs? How will it think about what to write? So, agents are basically capable of not just observing and identifying or working according to what humans wish it to do, but the core of agent is actually about autonomous decision making capabilities. Capabilities like now there is a need for a new program to do something. And also, all of this, as we are seeing, are intended to enhance efficiency, adaptability of the system, because otherwise we have one program, one software designed to do things. Uh, and whenever there are changes, either because of new technology coming in or because of the process of an organization changing, we know that in the past we had to redo a lot of things altogether. So the idea is that can agents help us in all of these activities by being autonomous and being adaptable, and also uh, solve a lot of problems on behalf of the humans. So it is quite essential to think of how we humans do it. So when we humans are agents of doing something, how do we do? What do we do? So in general, the few aspects that all of us have to exhibit is sense or perceive the environment around us. We understand language, and that's the communication. That's how we communicate with each other, and this will stand a big reason, big element in uh, actually realizing AI agents. Of course, we can reason about why we are doing whatever we are doing. We can plan about how, in what order we'll do a certain set of tasks, and we can act also. So we not only plan according to something, we can act. We can switch off a fan, we can go somewhere to fetch something, and we also learn over time. So we learn what is a time to switch off the fan correctly whenever we are feeling cold. We also know that this act cannot be that switch off the fan at 9 o'clock every day. It has to be based on the perception, the time, the temperature, and also maybe we won't switch off the fan even if we are feeling cold if there are mosquitoes around. So we say, no, go and better cover yourself rather than switching off the fan. So all these learnings, and these are not hard coded learnings, we sit in an environment, and then as we perceive, we go through all the cycles of doing something that is most advisable and most effective in a particular situation. So essentially, given that if we could have such kind of agents for different complex processes or organizational processes, it would be fantastic. Say, for example, legal and compliance. The court is flooded with cases. Can we do AI assisted analysis of court cases, detect fraud, at least fraudulent claims, uh, and only go for a select few cases to the human judges? A lot of cases are trivial. So it could actually do a lot of good if we can have the agents which are trusted, and we will know, we have to know that they can do it very correctly. That's very important. In healthcare, we are already using a lot of it. What we don't do is go from end to end, and I will stress on this further. We already have various diagnostic mechanisms, personalized medicine, and so on. But what we are talking about is, today a doctor uses something by actually evoking a particular service. Can we have end to end agents talking to each other and going through the entire drill of the service? Similarly for finance, so we do have algorithmic trading today. We have separately risk assessment, we have fraud prevention. Can we have all of them running along with each other to take a decision on our behalf? And also the decision has to be useful and effective. Cybersecurity, smart cities. I'll take many examples over here, what we already have and what further we can do if we have an agentic system in place for each one of these cases, which are pretty complex. They are not, none of them are easy, or a software like payroll, or even a face detection. It just stops at face detection. It has been trained to detect a face. You give it a face, it says yes or no, and that's about it. But we are talking about using a lot of these things in entirety. So here is one example of AI powered systems, I still call it, for smart cities, where we know and each one of these, by the way, have already got AI powered systems which are working. So my point of this talk would be what further would be available when we have an agentic system. So let me just go quickly through it. So AI powered sidewalk labs is a particular solution that exists for AI powered traffic lights, autonomous traffic routing if there is heavy traffic, uh, timing control for traffic lights, and so on. So that's one solution that exists, and all of these together are actually needed for a smart city. We have something for public safety and security, so surveillance through cameras all over the place. Even if we look at disaster prediction, we have a lot of some like flood prediction systems. Cyclone is coming, so which all areas have to be evacuated. So all of these systems exist, and together you can say they come under the ambit of public safety and security, a lot of which is already used. And I've given one example of a software which is there. There are actually many. Energy management, again, we have a lot of smart meters. My earlier company used to actually deploy smart meters for various clients. We have smart grid optimization, which is working on how much of power to draw from where, when, depending on the load. uh, we have energy optimized lighting solutions today, where when we walk into a building which is dark, it can sense and only then light up. So we do have a lot of facilities that are in place. We have water and air quality monitoring, and again, there are solutions which have been deployed in certain spaces. We have smart waste management. Waste management is a big thing, where we have software for sorting different kinds of waste, electronic waste, recyclable waste, and so on. And then also um, smart binning of this waste, and then working on schedule for clearing the waste. We, of course, have smart governance and citizen engagement solutions, which are including chatbots for public service and so on. So I believe all of these are familiar. Yeah, all of you know about these solutions in one context or the other. Uh, Let me first just go through another application, which is healthcare. Again, all of us are very familiar with the use of AI-based tools in individual areas of medical diagnosis, radiology, and imaging AI. A lot of them are doing it, marking the diseased tissues versus non-diseased tissues. Uh, Patient monitoring, it's a 24-hour service in ICUs, or also when patients are released from critical units, there are these software which are monitoring critical patients at home through wearables based health monitoring. We have treatments today like AI assisted surgery, robotic surgery, and so on. There are also autonomous soft tissue surgery using robots. There is an area which has been there for quite some time, which is drug discovery and development, which has the whole hog of discovering molecules, uh, proteins that are targetable to a particular uh, diseased gene, and then how to take care of it in order to uh, treat the particular disease. Of course, we have administrative and hospital management systems, where we also have logistics management. We have worked a lot on ICU management. ICUs are premium resources. We don't have an ICU per patient. So what is the critical condition based on which a patient should be admitted to ICU, and what is the expected number of days for which a patient will be there. We have found this is much better done by machine learning based prediction than doctor's prediction. We also have prediction of epidemiology, influenza prediction, how people are traveling when people have influenza, and therefore uh, what is the pattern of prediction has been used to predict which would be the next city which is likely to get it in an epidemic form. So various of these elements have already been worked on for quite some time, and all of these individual components are pretty much common. All of us encounter it in some form or other. So a quick look at what goes on to power these, and I won't be elaborating, but as we know, first of all, the sensing part of it. So a lot of it is happening through cameras, wearables, and texts today. We are interacting with the most complex of systems through either voice or text. So I find today that all the drivers can very easily use maps because they can't type, many can't type in English, but they can speak. And as soon as they are speaking, the search engine at the back is catching the particular term and the map is getting set. So sensing has become quite good and effective. Earlier voice to text was not so good. It's become very good, and these are some examples of sensing. There are others like monitoring body stress through sweat, and also ECG, and everything comes under that sensing part of it. Machine learning is a whole area which is doing a whole lot of learning of patterns and therefore using it for predicting. Also, along with it, today we have generative AI, which is not just predicting whether stock market will go up or down tomorrow, but it's also predicting a whole routine, a whole code, a whole drug, how it will be, how it should be synthesized, and so on. It's actually creating videos, so it's creating text summaries, and that's the generative part of it, which till about 2-3 years was not so good. Today even the generative aspect has become so good that we can no more say that creative generation is one area where humans do better than computers are gradually catching up. And so therefore a whole lot of generative tasks like summarizing a text, translation, video creation, uh, all of these have become quite common today, quite good. And so content generation is also something that's becoming going to the domain of AI. Uh, Code generation, if we think about it, is nothing but a type of content generation. And code generation is what actually is the basis for agentic uh, system architecture. That's what we will have to think about going down. Excuse me,
There is some disturbance, please.
Can I request others to mute, please? Okay, thank you. I can be heard, right?
Yes.
Okay, thank you. Okay. So one thing that we'll talk about is reinforcement learning. That is learning that's happening for an agent based on human feedback, because that's very important now if we have to go along to prepare or generate, as we were saying, code or sequence of code execution. And finally, one very important aspect is ACT. Okay. today we mostly use these AI agents, most of the cases, if you see, other than a robot doing a surgery, we mostly use these agents as enhancing the capability of humans to take decision. So we use a radiology image, we use an AI method on it to detect the area of the tissue that the tissue that is damaged. We are still a little reluctant to let a robo go ahead and delete it without human intervention. So the acting part, we still don't see a lot of it. We see it mostly in the first two parts, that is, the computers are sensing and then giving predictions. What we will talk more in terms of agentic is how will it also do some acting, like adjusting the traffic lights on its own whenever it can decide that on this route there's heavy traffic without possibly a human intervention, but do it right. That's the catchword. Okay. Can it control doses of medicine automatically? Again, as I said, we don't trust it enough today because the mechanisms are not in place where we can trust it totally. Part of the mechanisms are legal issues, but part of the mechanisms are also that we are not in a position to understand why it is doing what it is doing and how correctly it is doing. So incorporating all those mechanisms is what fundamentally uh, is different for agentic AI systems from normal AI systems. Okay, so with that background, are AI tools the same as AI agents? No. We have a lot of AI tools. They are task focused. They are capable of input processing, data analysis, and generating some prediction or some output. But what we see them are mostly user initiated, user guided. They are very powerful tools which can accomplish a particular objective. So, what are agents? Agents are what can do things in an autonomous and proactive way. Agents can use the tools, but just like we use the tools. However, they have to plan in what order they will act and how they will act. They will have to also manage workflows and then improve over time. These are very fundamental qualities of agents. So this is what can be defined as an agentic AI architecture. So there are these tools that we talked about. What does an agent do, or what does an agent have? So fundamentally, an agent should have a mechanism to observe the environment. Agent should have memory to remember what it had done in the past and why. And it should have access to tools, and more importantly, it should have goals, because we also, so I'll just elaborate on why each of these components are very important. With the use of all of these, and of course it can act, it will act on the environment. So what's an action? An action is such that when an agent makes an action or executes an action, the environment will change. So uh, if you look at it, this is a fundamental difference. When an agent predicts that these tissues are diseased, nothing changes in the environment. The tissues remain wherever they were. The doctor only has knowledge about where it is, but nothing actually changes in the cell unless there's some action. And mostly the action is taken by the doctor. What we are talking about is, can the agent itself take the action? So that's really the broader goal. So agent will have the autonomy to take a decision. Can it really remove the tissues? Can it does it have decision making capability? Does it have the power? And does it have the essential tools to do it? All of these are very important. Okay. Uh, we can have scenarios where a single agent can actually do all the tasks that are required. What are required, we'll come to that. But there are systems, when we talk about agentic solutions or systems, there can be single agent systems where single agent systems will involve one autonomous entity which will operate independently to achieve specific objectives. So, say for example, all of us interact with some personal assistant today, right? So, a personal assistant software keeps track of the appointments, reminds on time whatever it's supposed to do. You will see today, earlier in a calendar we had to set our own events. Today these calendars have become smarter, so they read from the emails and actually set up the meetings on their own. So these are also agents which are working silently at the back end, and that's what is different from a calendar program from a calendar agent. So a calendar agent is actually reading all your conversation and setting up meetings if it can understand that you have to attend this meeting at this particular time, and it can send emails on behalf of you to others. It can call. So whenever we actually install a software on our mobile phone today, the software actually asks for, can it send emails, make calls on your behalf, can it read your gallery, can it do this, that, etc. Because today's software are capable of taking a few actions, and that's what has changed. Of course, that is also dangerous. We don't want to give it the permission because we feel it can alter the things, but that's the power. It can read, it can write onto the uh, elements that it has access to. And that's where, merely from being informative program, it becomes an agentic program. We may have multi-agent systems. So personal assistants are single agent, but often the tasks, so if you think about the tasks that I showed, running an entire hospital in an autonomous way will involve multiple agents. So all those agents that I showed for treatment, for management, for ICU monitoring, you can imagine that they are all the responsibility of the individual agents. We already have them. Now what is required, that as soon as a patient is admitted to ICU, can there be and so there are these agents which start monitoring, and then can it predict how long it will be there, and then inform back the admissions department about what could be its stance whenever it receives the next ICU request. Today, a lot of this is manual. So, though there is ICU monitoring, a doctor is seeing, using some of the tools, but there's no closed loop in a hospital other than humans who are doing it. And that's why, and there are also many broken links in all this communication. So, we may need to have multiple interacting agents. In some examples, as we will see, the example I gave in the case of healthcare, these agents are collaborative. Whereas there can be situations where agents are competing. So imagine you have three different software for analyzing radiology images. Now, there are situations where one software is better. There are situations where another software is better. Maybe one is very good for uh, breast cancer tissue analysis. Another is good for, uh, say, liver cancer. Okay. Now, given an image, it should automatically detect which agent is good for a particular task, and it should actually get the information from all. There could be situations where there are three liver cancer detection or analysis software. codes. Now, agents should be using or may decide, that's a policy, you feel that they should be using all three of them and come to a voting mechanism or a way to decide which one is better. And in fact, when we do this, or even if you have access to all the three as a doctor, what you are likely to do is use all the three software, look at the explanations that they are giving as to why they have taken a particular decision, and then you decide based on your satisfaction. Now, if in your place there was an agent, it would just emulate what you are doing, getting all the three, getting the explanations, reading through the explanations, deciding where the agents are similar to each other, where they are different, and on the basis of this they'll take a decision. So this is a very typical scenario where you want multiple agent or a multi-agent scenario, which may have to communicate with each other, they may have to coordinate with each other, they may have to negotiate to achieve individual or collective goals. And with all of this, there's a possibility to enhance efficiency and scalability under different situations. Otherwise, we always humans suffer from this, that if I give it to a robot to do it, will it do it correctly? So how do I instill all of these features inside the agents? So from this point onwards, let me go into how this is done. So I hope I have established what is the difference between AI based systems as we still see them, most of them now. Even when AI is very powerful, AI techniques are very powerful, but we are mostly at a level where we are using AI powered systems. To move towards agentic AI systems, what do we have to do? So, this is the point where I start talking on the second part. Any questions? I can take them here. Okay, so as we mentioned that the first important part is autonomous. They have to be autonomous. So autonomous agents, if they have to take a decision on whether how they will go about doing it, the first important thing is to have a set of goals that they have to achieve. Goals guide the agent's decision making, learning, as well as interaction with the environment. So, goals are very important or foundational elements for agentic AI systems. They are the ones who guide whether a particular task is done efficiently and can be adapted better for newer challenges. So I give an example of what we mean by goal. So some, as you will see, very simple, some are complex. So we call goals as declarative goals, where you say what needs to be achieved. So there's a software like a thermostat, which is constantly running, where you say maintain indoor temperature at 22 degrees C. But you add a constraint on top of this because it's an AI system. It should take up more challenge. You say with minimal energy consumption. Now this becomes complex. It has to do it, but it has to do with minimal energy consumption. So therefore, at every point of time, it has to see how much energy it is consuming in order to maintain the temperature, and what would be the best way to ensure that it can do it with minimal energy consumption. So that becomes target, but it's a very well defined target. There are task completion goals like generate reports of EV charging patterns for a city, electricity pricing, and grid load of a region. So now here it's actually multiple tasks, right? So you have given it a task, but when it has to decide whether it is doing it correctly or not, whether it is done it completely or not, it has to break it into smaller tasks like EV charging patterns. So it should understand what's a pattern. Pattern is basically a temporal trend marked over maybe a month or 6 months or a year. It has to also go for the electricity pricing, which is from a different source altogether. It has to get the information and grid load of a region. So you immediately see that when you tell it to do it, there are so many different steps to do it. Now, that is one thing that the agentic system will do. But the way you have specified, it can verify whether it has got everything or not. Okay, so that's where it has to complete a set of tasks which are well specified and but complex. Optimization goals. So here also you say with minimal energy consumption, so that's also kind of an optimal, but here this is much more concretely stated that all this exercise of monitoring, surveillance, gathering of energy reports, etc., is basically to improve performance of the organization over time. So now you cannot just say improve performance, you have to give it goals and targets to meet. So you say reduce power consumption in the data center, and it's very easy to measure. If it was so much kilowatts in 1 month, after 6 months of all these agentic AI, you check whether it has gone down. If it has gone down, you say it has satisfied its goal. If you put further, you say reduce energy costs. That means it's not just power consumption, it also has to go to this energy pricing and from whom the energy is bought, etc., etc. And then you say that the total energy cost has to go down by 15% in next 6 months. It's again a very tough goal, but all of this will involve a whole lot of actions, and at the end of it is very measurable, that whether through this you have gone down by 5%, you have gone up by 5%, or you have reached this 15% in 6 months, or maybe 10%, but you feel now a little more tweaking here and there will bring it down to 15%, if not in 6 months but 9 months. So this is exactly how humans will approach doing a problem, and we want to see how this can be achieved. And there are exploration goals, which is not an action, but just identify. So identify the best times to charge electric vehicles based on grid demand. Once you have identified, you give the times to the owners, and they will decide whether they'll act on it or not. So that's also a kind of goal specification, exploration goals. On top of it, we also talked about multi-agent. So multi-agent goals may have these coordination required. So therefore, you also mentioned that you want a balanced power distribution between solar panels, batteries, and the main grid, where each one of where one agentic system may be responsible for each type, and they have to coordinate with each other actually to achieve that minimal energy cost, or minimize energy optimized energy use, and so on. So in between there will be a whole lot of coordination required among different agents. No single agent can achieve it, just like no single human being can actually achieve these kind of tasks. And then there are adaptive goals, where the agentic system is not given such a specific thing like reduce by 15% over 6 months, but it's a continuous thing. So continuously adjust HVAC settings for a building based on real-time occupancy and also weather conditions. So it doesn't end anywhere. It's not achieving a report or achieving it after 6 months. It's a continuous process, and with all the climate and weather factors changing, this never stops. Okay. So very grossly looking, once we have gone through these different kinds of goals, we can see how a developer can go about designing such kind of systems. That's ultimately the aim. So, very broadly speaking, we can say that what today's developers need is, when it has to design an agentic system, it has to first have a very clear understanding of what the declarative goals are. That has to be a high level system objective. Specify any optimization goals that may need to be there, and also integrate learning goals, because as we said, there is an adaptive changing that may be required. Now, having given these, this is very easy to understand. If I have to design a system, I have to specify what it needs. So for agentic systems, we need to define goals, not just input and output. That's the difference. Now, if we have goals, then what will the agent do? If we tell the goals to be achieved, then the agent has to break it down into operational steps for implementation. And from there onwards, this whole thing about how will it do it, that's the part that starts. If you give it optimization goals, then it has to identify reactive goals, but what that is action steps. It will have to identify what are the different kinds of actions that it will try out for optimization goals. And learning goals, how does it learn over time? So this is a schematic representation of an agentic AI system. So on the left hand side, you see as an agent perceives the environment through different kinds of sensors, monitors. That's what goes into the perception system. Over there lies all the analysis part, AI based analysis, that machine learning, whatever we have. But now comes the most important part of agentic AI systems, where we talk about the cognitive component of the agentic AI, which is actually responsible for the planning and the reasoning part of it, to decide what is the step that will take me one step closer towards the goal. So, over here actually is the major emphasis of how do we design such cognitive components which can plan, and while planning it has to apply reasoning, it has to apply all the tests to check whether its plan is solid or not, and then only it gives commands for execution, which are called actions. Now this part, uh, these two parts, analyze and action, are easy. So already we know there are switches which can automatically go down or sense and then set the temperature and so on. So what is more important is how all of these are designed. So let us first start with, we said important part is to give goals, and based on goals, the brain will decide what is a plan and execution plan. That's what. So it will have to take into account whatever execution plan it has. It should be able to perceive the environment, and there has to be some or the other component which can deal with the inputs from the environment. So let us look at, so what does it do? What does such an agent do? An agent actually plans based on what it can do or what it needs to do to solve a complex problem. All of this has to be built in. Now, when we talk about built in, pretty much what we also do, but it has to have a structure for doing it. So internally, goals like this are broken into sub goals using what is called a goal tree structure. The goal tree structure learning, how does it learn? What is this goal tree that will lead to the actual execution possible, is all that is about agentic AI. So How does it generate this goal tree? Where at the lowest levels of this tree, there will be some action that it knows that can be executed through some component. And as I said, if you think about what we were talking about, the AI components, you can pretty much think about those components are what are at the lowest level. That is things that we already have. What is important is how do we break this high level task into various lower level tasks? How? And each of these lower level tasks can be further broken into the lower level tasks and so on. How long will you carry on? Till you reach a point where you have components to do each one of these tasks, and then you can verify against completion of goals whether all the tasks have been completed or not. So pretty simple idea, though not very simple to execute, that if you have a complex goal, you learn to, the agentic system learns to find the best execution paths by building goal trees, where ultimately the trees are such that there is a path which will lead it to the leaf nodes where actions can be executed, and together all the actions should be able to satisfy the task that was given to it in the first case. Okay. So obviously, what will a logical agent, logical thinking agent do? It will outline all necessary components to achieve the goals, order them, identify dependencies and constraints between them, and then link them all by logical relationships, like in order to do this I need to do that. Okay. A very simple example and a very classical one for AI is chess. We all know the first successful AI program was actually playing chess. Now if you think about it, what or how does it play? It actually has at the back end a state of the board. Now the computer is one of the players, the human is another. It doesn't know what the human will do, so it has to perceive what the human has done, and then based on that it has to now expand the tree further as to what are its possible moves, with one goal in mind always, that how will it reach a checkmate. Its goal is always the checkmate, but the paths are, there are different paths, and the path is not entirely under its own control because it's not a single player game. Path is decided by the computer as well as the opponent, and depending on what the opponent has given, it will further internally in its memory, it will lay out what are all the possible things that it can do at this point of time, and then has to see which one is likely to lead it to the end, or the win correctly. Now obviously, since there are too many possibilities and it cannot do a very exhaustive representation, so therefore all the intelligence that can be put in comes into place. But still chess is a comparatively restricted environment where the rules of the game will dominate, and there are no randomness in the environment. When we are talking of agentic systems like healthcare or smart city, there are too many random variables that are in place, which cannot even be specified. So today being a day of weddings in Delhi, all roads are very busy. Now this is a very sudden thing that happens on some days in November. Similarly, for air pollution, suddenly on Diwali day it goes up. So it cannot be really thought of that what are all the situations that can lead to a particular state. However, the idea is very similar. Only thing is it's a dynamically growing environment, dynamically changing environment, and at every point the agentic AI has to build such a goal tree given the conditions, and it has to learn what's the best possible path to solve it. Okay. Now, what we have today is basically, for all of these things, we have the LLM coming into our rescue. So, why LLMs? What exactly is the role of the LLM to generate this action sequence, and the, or how is the LLM used? LLM stand for large language models. I'm sure all of you are using ChatGPT or even simple search engine. You see, it's now giving you some answers which are direct answers to your questions and so on. So how does this now come into help to execute these paths? So for that, let me take a simple analogy, an example of what we do. Do we, when we act, do we think, use our language to act, or do we just go and act using our hands and feet? So these are some actions which we have to do. Say, hang a picture on the wall, paint the fences, change tires, open a wine bottle. These are all actions that we do. If we think about it, how do we do? How do we go about hanging a picture on the wall? We know the steps. We look for the steps, as in, what do we have to do? We have to first put a nail on the hole. In order to put a nail on the hole, we need a drill, and then we need a hammer to push the nail on the wall. So because we know the steps, and we have a toolbox at home which has all these tools, we also know the description of each of these tools. We not only know its shape, there's an internal linguistic representation of this shape in our head, which says, you have a hammer, you have a spanner, you have a wrench, and what each one of them can do. So if it is for drilling a hole, then you will first look for the drill, then you will look for the hammer, and then you will hang the picture. So this is a sequence. This is the role that language plays in our minds to decide the sequence. Though we don't think about it, most of our actions are actually guided by language. What if you didn't know what to do, a particular task? Then, of course, you would Google. So, how to open a wine bottle? If you didn't know, you would Google that which particular tool in this toolbox. It has 100 tools. Then, what to do? So, Google will actually tell you which tool to use. And then again, you go to your toolbox and match or find the tool that matches the shape description of what it has shown. So either way, the point is that we will first need the steps, and we will need a descriptor to match along with an available set of tools. Now, if you didn't have the tools, no amount of description will help. Okay. If you have the tools, but you didn't know which tool to do what, then you need the description. And the moment you have the description, you can go and pick the tool to do it. That is precisely what an agent framework is doing. When it has a task, it can break it down, or it can ask a large language model to break it down into subtasks. Still, it can find tools to solve the task. What are tools? These tools are called components, and tool discovery is aided. So basically, they are programs which can execute, which can do things, whether they are programs in a particular language, in embedded system, or wherever it is, they are capable of doing something. Now, what we need in an agentic framework is like a toolbox, a library of tools which have description to say what the tool can do and how it does it. So now, if I have to do a web search which is part of, say, I'll just show you some examples. Then a particular tool which can do web search on behalf of the agent has to be found. That's all. So this is why we say that if you give a complex task to a robot, let us say, and a robot internally has access to an LLM, it can access the LLM with the goal. The goal statement is there that you give to the robot, that this is what I want you to do. It will have access to an LLM, which will help it break it down. And of course, there is some amount of mathematics that it will have to apply in order to know that whether a set of actions that is satisfied, given by the LLM, whether they are optimal or not, whether they can be done or not. And that is the entire aspect that goes inside LLM based reasoning agents for powering agentic systems, which can do quite complex tasks. So, what I have said is, if you give the set of goals or a goal to an agentic system, it will try to generate a plan based on the goals. The plan is nothing but that goal tree and a path in the goal tree that is going to satisfy all the requirements. This task of planning happens in many ways. Could be without any feedback. So given the goal tree, it will just call a set of agents to do a particular task. And today there are a lot of agentic systems. Like I said, you can perform web search on your behalf using an agentic system. There are maths problem solvers, uh, whatever. There are a whole lot of agentic systems which can do this without a feedback. And there are more complex agentic systems which will actually use feedback internally to decide whether or what is the best path to do things, because it needs that. So think for a while autonomous driving agentic system which sits inside self-driving cars to do autonomous driving. Obviously it will need a lot of feedback from the environment. Just one set of actions will not lead it anywhere, and it's not safe. And similarly for all the other kind of scenarios that are mentioned here, where agentic systems with feedback becomes important. So first, let us look at how planning without feedback is going on today. So as I mentioned, it could be as simple as give it a goal, which is a prompt. Let it break it down into steps using the LLM itself. You can train the LLM a little bit to do it in a particular way. So here are examples. So this is an example of a zero shot prompt. We just tell the LLM something we all do. Imagine you are a history teacher doing it. As an example, let us say you give it a maths problem, or say that, calculate what should be the optimum temperature if the outside temperature is this and there are 5 people inside the room. It can have access to a calculator and it can tell you. However, it's not always so good zero shot prompting just by asking it to do something. So the concept of few shot prompting came in, where you give it some examples. I have not taken complex examples here, just saying that it's supposed to be deciding whether something is good or bad, positive or negative. You actually give it some examples of what you think is uh, negative and what you think is positive. Okay, this is weird because we don't usually think of this as bad as a positive, but let us suppose this is a feedback loop where you want to know what can be improved, and you are really looking for negative feedback. So therefore the negative is positive here and the positive is negative here, which means you are trying to change the learning of an LLM. Give it some examples, and after that it actually starts doing things in a particular way where you want it to be trained in a particular language. There are these other kind of prompting which are becoming very popular, which is say chain of thought. So not only give an example, like this is a unitary method and the LLMs were very bad in maths, even when it was just given some examples as, the answer should be this, it was wrong. But when you start telling it how it should solve by writing down the steps exactly as a third standard student will start writing out the steps for solving a unitary method problem, then it starts giving the correct inputs. So this is an overall example that if an LLM is just asked to generate the sequence of actions, it may not be so correct. If you give it a few examples, it may be correct in quite simple scenarios. It performs much better. So it's found that it hallucinates less. When you actually give it chain of thought or tell it how to do by giving illustration, step by step illustration, it has been found that they can be very good in executing tasks and their efficiency goes up remarkably. So here is an example of a real agent developed at EPFL, which is for AI powered chemistry agent for uh, drug discovery and materials design. So it has to come up with these designs. And as you appreciate, these designs have to be error free, they have to be safe, and they cannot just suggest some kind of molecules interacting with other molecules, which is physically not possible. So all of these can be built in, provided all these, some of these constraints are given to it in a way uh, so that it can learn how to do. And this has been used with chain of thought reasoning loop, where it was told through examples what it should do. So say, for example, if it has to find a particular um, drug, then it should do a web search for certain kind of whatever other drug names or the input diseases, etc., that is given. It should do a literature search. Now these are steps which we all as humans do, but now it's possible to incorporate all of these into an agentic system right up to the search for the right molecules, because there are already a lot of chemistry tools, and now all of these are integrated. So as you see over here, this is a list of tools: smiles for weight, price, CAS, similarity assessment, modify molecule. So all of these are tools which are there in order to assess, in order to use, as well as assess whether the results are correct or not. Okay. So this is an example. Let's say, uh, how can I synthesize aspirin? This is a test question. Now, without prompting, just an LLM, large language model, gives some answer. It cannot be verified for safety. Now, the researchers check that when they do it, of course, they just didn't train it for aspirin. It could be for anything. Now, when the prompt is given as let's think step by step, then the response becomes much better, because this is how it was trained. Very few examples are needed to train, maybe about 10 or 12, and then it automatically learns to generate much correct answers. And that's the power of LLM, because all these things, choose a reaction mechanism, specify reaction conditions, these are pretty standard mechanisms. So now what has happened is, such a synthesizing activity can be now uh, simulated by an agentic system which knows what are the steps, and ultimately there are these chemical tools already available for each one of them. So now the task goes for these agents to use these as the inputs and call the right agent to synthesize it. Moving from, but as you see in this whole thing, after the first training with chain of thought, there's no further feedback. So at this point, the end users are only using chemcrew to give their synthesizing molecule. That's all. And it's generating these kind of answers. However, as we mentioned, there are certain kind of scenarios where feedbacks are important. So the first generation of agents which now not only learn to break a task and execute, but also takes a moment to reflect and see whether it has accomplished it all or not, having a think component in between, is the planning with feedback agent. So if we think about it, it's actually, first of all, the first part is same. It's exploring, refining, or breaking down a complex command into a set of commands. Then it has some amount of training to generate a plan. But now what it does is it's evaluating this plan. So if this had come from for aspirant, it will evaluate this plan. Now, how does it evaluate? Is it a human feedback that goes on, or is it the LLM itself or the agent itself that will evaluate it? So that is the next two generation of agentic framework. The first generation was feedback and self-reflection to see whether it was complete or not. So it does it by looking at, measuring whether it has all the aspects of the answer or not. So this is an example. If here complex questions are asked, it just first does an action, like you see act 1, whatever is the answer that comes out, it then evaluates it, okay, and then decides what is the next action that is to be taken. So this thought is the part of reflecting on how good or bad it is. In this case, it's a complex question. Aside from the Apple remote, what other devices can control the program of Apple remote? So what other devices? It's a search. So it's searching through a repository to see in the past whether there, what were other programs and so on. And it refines it. So in the first case, it sees a software name. It goes and searches by the software name, and then as it sees that no answer is coming out, so it sees, then it refines the query and then goes on to get some more answers before it gives up or gives a junk answer to the end user. So React is a framework which has been used to design these kind of agents. Particularly, there are complete web shop softwares now where a user like me doesn't even have to spend time on going to Amazon, going through all the products and seeing whether it suits me or not. I can just deploy web shop, that's it, and say that buy a pair of black shoes for me, okay, and that is uh, so it's expected to go and come back and tell me that your order is placed and it will come day after tomorrow. So that's already in place, and a lot of web shoppers are using it. We go to the last part, which is planning with feedback. But now, rather than doing a self reflection, we have many more features now coming into place, where the first thing is, in very complex scenarios like optimal optimization decisions, Now, optimization decisions by nature means various alternatives have to be explored. What we saw in these earlier ones where there is a path to refine gradually. So it starts with something, it goes to the next step, next step, next step. It's a gradual refinement to do it. Whereas in optimality, what we need is, to begin with, the agent must explore multiple paths, need to try multiple options, evaluate, and then choose the best one before it goes to the actual execution. So we earlier saw chain of thought. There's also another kind of prompting that is gaining foothold now, which is called tree of thought. So a tree of thought prompt analyzer is trained with multiple paths, and also along with the paths come an evaluation function to decide what is the cost of this path. So what are the elements on which the cost will be calculated, will be given. So as you can see here, what if you have asked it to explore something or give you an optimal answer? It has explored three possible sequences. One of them, and so this is the goal you have given. These are the sub goals. Each sub goal has different ways in which it can be accomplished. Uh, this one, the green path, is found to be the best path according to whatever constraints are given. Let me take an example. So plan an optimal delivery route for a drone delivering packages to 3 locations while minimizing travel time and ensuring that the battery lasts the full trip. So what it has to do, 3 locations, let's say they are ABC. So it will at the first instance explore ABC, uh, CAB, BAC, and for each of these, if it is taking this path, what would be the distance, what would be the battery drain? That's what it calculates. It finds that this path is landing in the shortest path, battery drain is medium. This one has heavy traffic, battery drain is high, and this one actually has a no fly from A to C, so it cannot even do all of it. There are other possibilities, so it can explore. And now, over time, the idea is that in such complex scenarios, there's no one answer, of course, but to some extent, it can look at its own evaluations and decide on the paths. And then it can also work on a kind of reward assignment, where the rewards are coming from the environment itself. It can come even from humans in the loop. So while at the first instance, it will suggest that if you give it this after exploring, it can suggest that this is the short explore ABC. A human may give it some additional inputs and say, okay, ABC at this time, but other times it can be BCA. Just explore and see whether it is feasible or not. So that is where we have other kinds of learning, like policy gradient optimization or reinforcement learning, with giving some scores to this path whenever it's achieving really the shortest time, penalizing it if it's not achieving it in good time, and so on. Over time, it is supposed to learn, and that's the adaptability part of it now, that while it is intelligent to explore and suggest the best alternative as it appears now, over time, with reinforcement, where we always give feedback. Did you receive it on time, or what was the time in which it was given? So self capturing of a lot of parameters can lead to actually learning from rewards and unlearning paths if they are penalized very often. So there are agentic frameworks today which allow for these kind of learning also. So depending on what the application is, we will select a framework like a simple one with chain of thought, or a React framework which does automated evaluation of plans internally, but gradually goes on refining, or maybe actually Rex kind of framework where it's possible to give in external inputs. These are this is another framework, retroformer, which actually goes for heavy amount of reinforcement learning and is ideal for situations like smart grid management and so on. They use Monte Carlo search methods at the back end to decide on the paths even before starting to work on running a particular agent plan. I'll end. Before ending, let me also talk about what is the current research, and it's about learning the action language itself. So these are some very heavy frameworks where the idea is to learn action languages or action paths, not just, as we know, today's language is learned from whatever texts we are writing. Action text is different, and these can become even better agentic platforms for doing tasks. So I'm just glossing over them because these are too much of details which may not be so useful. So broadly, what I have spoken of is how AI has evolved today from just era of machine learning, where we could do some cancer cell detection, to era of large language model, and how that is being used for designing sequences of tasks, where we are talking today in a position to talk about adaptive control and continual learning through feedbacks also. Of course, there are potential risks when we say agents themselves will decide a schedule and pick up an agent based on the description and so on. We have to be careful that there are agents which have been planted by somebody, which is actually a fraudulent agent or a corrupting agent, just like viruses were there. So, how do we even know that these are harmful or not harmful before an agent picks up, or whether agent is actually trained to do something harmful? So all these things will have to be thought of. We do have today agents which can access databases. Now we have to think databases were actually initially designed to provide controlled access, and is it the right thing to do? So while it's exciting and it can be useful for very complex engineering tasks, that's indeed the advantage, because as humans, internal of an engineering system, viewing in entirety all kinds of situations often become impossible. But an agent can do it much faster. Even things like drug discovery, what all combinations are possible, it can do it much faster. So actually, chemists say that what used to take 6 years can be done today in 6 months. Uh, that is the kind of speed that is possible to be done. But let's think really hard before we act. Thank you very much. I'm open to questions.
Thank you, Professor Lipika De, for your excellent lecture and introducing even to laymen like me on the topic of agents problem solving, intelligent agent for adaptive and autonomous decision making. Right from the fundamental, you started it, and it was really very, very enjoyable. And most of the things I could understand. Thank you.
Thank you.
So now actually we'll, the thing is actually open for certain questions and answers.
Sure.
If our people have, Professor Sanat Kumar is here. He will have always some questions to ask.
Yes,
Thank you,
sure.
sir.
Yes, please.
Madam, your lecture was fantastic. As Dr. Acharya said, I could also understand part of it anyway. But compared to you, I am a fossilized person fundamentally. I will raise 2 points before I give it to you back to answer. Number one is trivial and humorous from your point of view. you know, I order, you said, you order black shoe. So I order black shoe on Amazon. Then when I receive it, I get it brown. So now I have a problem. So I call a, voice fellow or, somebody who attends to telephone calls. He said, I will connect you, sir, etc., etc. Ultimately, nothing happens. Then I send an email. Now, here comes the problem. The manager who's to attend to the complaints has a personal secretary. Okay, like exactly like what you said. The personal secretary is a bot, and that fellow says, "This is a computer generated thing. Please don't reply to it. Our manager will reply," and that reply never comes. So this is one system I wanted to tell you. The next one, which is slightly more serious, is that in my service time, we used to have a system that has to go step by step by step by step, 1,000 steps it has to do to complete its job. Now each step has got sub steps, and each sub steps has got, we used to have hardwired devices, temperature monitor, pressure monitor, etc., etc., etc. And its feedback is compared to a comparator we have, a PLC or something like that. And then based on rules that we have written, it will say go or no go. So go means next step it will go. So 30 steps like this make a program, and 8 programs like this make a entire job. Okay, so this is what we had. In that, very often multiple things can go wrong.
Yes.
The temperature switch is not telling the truth, the pressure switch is not telling the truth, or some potentiometer is not telling the truth. So something fails. We were interested to know how to do troubleshooting. In those days, I was trying to do troubleshooting. Some computer knowledge I had, and that I was trying to do very, very simple DOS kind of fellow. So I was trying to do troubleshooting. I never got along with it because single failure is fairly easy. A experienced operator can see the control console and say, okay, what has gone wrong. But if it's a multiple failure, it's very difficult. So we were trying to, this was our inputs for AI at that time, long ago, nearly 25, 30 years ago. Now I come to the third point. Your AI agent, is it running on its own computer, or it's a computer program, right? So it must be having, are you running it on your own computer, or you are running it on a standard IBM or anybody? Then if you are the latter one, then if the computer fellows keep on changing their operating systems, they keep on upgrading, they keep on doing something, they even change the chips, etc. So what do you do for that? How do you know that you'll have to start reinventing your AI program? Thank you.
Thank you. Excellent points, actually. So the first one, email, that is, that is still not agentic. So what happens is, it's a robotic thing that as soon as a mail comes, you just shoot off an email. And that is where we say that, it is the first step which has been done. But there is no check on whether it is resolved in 4 days or not, and so on. And so therefore, this whole validation, verification, which are also parts of it, is coming up in order to, and it should not only inform me, but it should also inform the supervisor that these are things which are not done. So that part is sort of solved. But the other part that you said, that there are complex rules and all of that. Now precisely, first of all, what people have done or what people are doing, like maintenance people's notes, are extremely important inputs to the agentic systems to learn the way to explore what kind of things to look at. So when we build today's machine learning based predictive intelligence system and so on, they are the ones who give a lot of insights about what to do, because they learn the different things that people have tried. Now, what is the role additionally of LLM? Now, different maintenance engineers or across organizations or even across departments in the same organization use different languages. Okay. Now, when we have these language models, they resolve these differences and also help in quick search of a very large space to look for possible answers. And then comes the part that you said that this is still okay to decide, one point of failure, but now comes the simulation part, that they can actually try the combinations that are possible to see which was not possible for humans, to try all possible combinations. Now, because it's AI, it can simulate and try all possible combinations and suggest what could have possibly gone wrong much faster and easier than what humans could do. That's precisely the point. The third point that you mentioned, that whether we are running it on different places, yes, that compatibility issue. Now, those are issues which come at tool level, because ultimately, I may have used a language which is not compatible today, version has changed, and so on. Uh, now, those are last mile problems. And again, what happens today is we look at all the tools compatible with the version of OS and language that we are using. If it is not there, then we have to additionally build it. Absolutely.
Yeah, because this become outdated very soon. Uh, Windows 8 doesn't run anywhere nowadays.
Yeah.
So I have old computer running Windows 8. So that is
Yeah.
the problem.
Yes.
Yes.
I mean, hopefully still there will be things for humans to do. That's really the advantage.
Thank you, madam. Thank you.
Okay.
Yeah.
Thank
Thank you very much, Professor. I'm a
Okay.
biochemist. Is it okay if I can ask the next question?
Please.
Yeah, okay. So I'm a biochemist and I'm trying to utilize this AI for complex decision making. So I have few series of questions to begin with. Uh, when we choose, how do you actually choose the right LLM for your agent? Because there are so many options available.
Yeah, so there are also these, LLMs which have been trained on bio literature itself. So that is one of the things. Also based on the resources that are available to you, that how big a model can you use, and a lot of this discussion goes on today, that whether it's really good to use a very large general purpose LLM or an LLM which is suited for your kind of tasks only. Okay, so it's guided a lot by uh, further training of or fine-tuned models that may be best for you. Okay, but as you saw, ChemCrow is built on top of GPT-4. Okay, but their library of tools is what is very specific to them, and the descriptions that are accompanying the tools is what is helping them. Now, going along, we'll also have XLM that is trained on agentic language. Okay, so yeah, I don't have an answer for you. It's very much a trial of what you want to do based on your requirements. It has to be selected.
So, given this prompt engineering, do somebody who's not a computer science person, do you still believe that one has to learn computer programming to be able to explore this AI agents and LLMs?
Not programming per se, but has to learn. Has to learn how the prompts work. The second part of it is, you will have to still learn how to verify. Okay, that if it is giving an answer, how do you verify? And these are there are tools, a whole lot of tools are there. So I won't say you have to learn computer science, but I'll say you have to learn computing to know how things are working and how best to make use of different kinds of tools. So what is a tool that will generate whatever you want. What is a tool that will verify what is generated? Okay, what is a tool that will actually tell you that how safe it is? And I don't know all the tools being a computer scientist, but in your area there will be a library of all the tools and their ratings. Okay, so in fact I didn't show that slide, but there are all these agentic platforms along with ratings on GitHub coming from various users to know how reliable it is and where all it fails.
Okay.
Okay, also I would definitely like to say that having humans in the loop is becoming very important for all critical applications. Okay, and when we talk of agentic framework, in fact having the human in the loop is also a part of the framework. Only thing is,
Okay.
you don't want humans to be everywhere. Okay,
Mm.
and you want the inputs from the humans in a mathematical framework, that is reinforcement learning. That is, for everything you want a you know penalty or a reward. Is it correct, is it wrong? So yeah, we are not dispensing of the human, we are just saying that exploration can be done by agents, and uh, they will not show everything to the human. They'll do first set of validation so that the human load becomes much less.
And there was this one concept where, in the very beginning, you had said that the tools can be utilized to do your entire literature search and web search. So that was very interesting for me because, uh, compared to a human, that's the advantage which
Absolutely,
this.
there are all these research co-pilots. Okay,
Mm.
who will do it, so it knows what you look for when you are reading a paper. Okay, if it's bio, it will know that maybe you're looking for case study. If it's a case study, you're looking for how many subject, what is the method, what is the analysis. So it will go through all the subjects, all the papers, and generate a very structured output for you.
Okay. Thank you so much for your time. This was very beautiful. Like the way you've taken us through this journey, so exhaustive and very beautifully articulated. Thank you very much.
Thank you so much.
Okay. Any other question? Anyway, I think there is no more questions. So first of all, from the organizer side, I would really like to thank Professor Lipika De for her excellent lecture, and it was also coupled with beautiful questions from two persons, but they were quite extensive, and it was really excellent to listen to her. Now, this series of lecture is being organized by number of institutions jointly, that includes INAE Bhubaneswar chapter. It includes IIT Bhubaneswar, Niger Bhubaneswar, IMMT Bhubaneswar, then this SOA University, which is really hosting this one, and very recently, two other organizations have joined also hand with us. One is Institute of Chemical Technology, Indian Oil Campus in Bhubaneswar, and IEEE Bhubaneswar section. So it is a joint effort of so many people. I must really thank them for helping us actually to have this series of lecture. Now, one more thing what should I like to say, that though the number of participants have been few, but definitely right from the beginning, those who are there, they still continued to the end. And this only shows the quality of lecture and the quality of presentation. Thank you very much, Professor Day, again. Now, one or two small things actually I would like to ask. First of all, your lecture has been recorded. Do you have any objection if could be shared with others?
No objection.
Okay, thank you so much. Now the next thing actually which I'd like to say, that so far as this INAE Bhubaneswar chapter is concerned, we are not in a position to compensate your time and all these things, but definitely we'll send you a small memento by post to your place. Thank you so much, and thank you all those who have really attended this beautiful lecture.
Thank you all. I was not expecting any honorarium or anything. It's always very interesting to talk to.
No, it's okay. This is a small courtesy from our side. Nothing more than that. Is some sort of gift will come to you.
Surprise. That's a very pleasant surprise. Thank you.
So, Professor, you did your bachelor's also from mathematics department of IIT Kharagpur.
Yes, I was in 5-year integrated MSc.
5-year integrated.
Actually in Anurag Acharya's batch, if I don't remember whether I told you.
Pardon?
Anurag Acharya, you knew him?
No, Anurag, this is actually Professor H.N. Acharya's daughter.
Okay, yeah. So I was in Anurag's batch.
Okay.
So, yeah.
So,
5-year batch.
So you were born in the campus or
no,
from outside you came through
outside.
the?
Yeah.
Okay.
Yes.
And who was the head your time? Professor G.P. Bhattacharya?
No, it was Professor J.R. Rao.
Professor?
J.R. Rao.
Oh, J.R. Rao.
Yeah, Professor GPP also became a head, but it was later, like in our 4th year or 5th year.
Professor J.R. Rao was actually my neighbor.
Yes.
Anyway, a great professor.
Yeah.
So it was really a pleasure to listen to you and to know that you have, very good connection with IIT Kharagpur, where I have spent 43 years of my life.
Yeah, we were also there.
Thank you so much for joining.
Thank you, everybody.
Okay, thank you.
For questions.
Bottom side,